Welcome back to our journey through the incredible story of Einstein's general relativity. In part 1, we explored the early years of Albert Einstein's groundbreaking ideas. As we move into part 2, we find ourselves at a crossroad in Einstein's life and career. Will Einstein choose to stay in Prague with his wife or move to Zurich, where new challenges and opportunities await? Today we delve into this pivotal moment and explore the fascinating pages of the Zurich notebook where Einstein's thoughts and calculations began to shape. You will also witness the struggle of a genius as Einstein grapples with the complexities of Tensor Calculus, a field he was not yet fully familiar. We will uncover the story behind the Entwurf paper, a significant step on the path of general relativity, and the crucial collaboration documented in the Einstein Besso manuscript. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the part 2 of Story of General Relativity. Before we move ahead, here is a quick recap in case you have missed the story in part 1. In our previous video, you have learned about the profound impact of Einstein's 1905 paper, a seminal moment in the annals of physics, reshaping our understanding of space-time. Einstein's journey, as elucidated by eminent Professor John Stachel, unfolds in 3 distinct phases. Apart from his scholarly pursuits, Einstein savored the rich cultural tapestry of Prague and engaging with its vibrant and intellectual milieu. You can go to my previous video where I have actually demonstrated how he mixed with Franz Kafka and spent some time at this cafe, which you are seeing right in front of the screen. His intellectual prowess manifested in groundbreaking papers that would revolutionize our understanding of the cosmos. The different coffee shops, the places that I have visited, Einstein visited in Prague, I have given a fair good account. You can go into part 1 of the video and look into it. Einstein's conceptualization of gravitational potential as a static singular scalar function marked a pivotal moment in theoretical physics. As you can see that I have already demonstrated that the energy of the gravitational field can act as a source of gravity, and in this paper and his writing in Prague, how he formed and was trying to find some of the observable effects of his theory. Here, as you can see, that there are static gravitational fields and the single scalar function, which was actually a kind of a problem and which was later encountered in his later papers, which we are going to look today. So it was covered in the first part. And also, as Einstein departed Prague, tensions shimmered with his personal life, with the discord arising between him and his wife Mileva, who yearned to return to Zurich amidst a cultural disquiet where there was mostly the German people community. We ended the part 1 of the video where we found that Marcel Grossmann, a longtime friend of Albert Einstein, was appointed as a dean of the mathematics physics department, and he was actually trying to call back. But Einstein got an offer from Utrecht and Leiden, and he was in a better position to go to Lorenz, with whom he can work on his mathematical endeavors. Now, in spite of that, Einstein moved from Prague to Zurich. And was that a right decision or not? That is what we are going to take from here into the next part of the video. Zurich, 1911. During his entire span, here you can see that the entire span which Einstein stayed in Zurich, he produced 3 seminal documents that significantly advanced the search for a theory of general relativity. The first one is the Zurich notebook, and this is actually a small notebook which contains some of the Einstein's private calculations, but it is very, very important in understanding the development of Einstein's relativity. The second, equally important, was the collaboration with Marcel Grossmann in producing the Entwurf paper, and this paper was actually contains, I would say, all the essential elements of general theory of relativity, and the last one was the Einstein Besso manuscript. It's a collection of 50 pages. I'm not going to say what it contains, but something very, very crucial and important in our understanding of general relativity. So these are the three documents which we are going to look in today's video. Most importantly, these are the most important seminal papers which shaped the our understanding of space-time and the formation of general relativity. The Zurich notebook which Einstein framed. So first of all, let me show you some of the screenshots from Einstein's Zurich notebook. So these writings, scribblings and notes represent the seeds of ideas that would ultimately change the course of history of science. Each line and equation penned in this notebook paved the way for revolutionary breakthroughs leading to the formulation of the theory of general relativity. The seemingly modest pages of this notebook hold within them the genesis of concepts that have profoundly reshaped our understanding of the universe. Now, if I go overall, the idea of the Zurich notebook, so let me tell you. So first is that the Zurich notebook captures Einstein notes from the crucial immediate phase of his quest for a relativistic theory of gravitation. During this time, with the assistance of Marcel Grossmann, Einstein delved into the concepts and methods of tensor calculus and Riemannian geometry. So as you can see, it contains around 96 pages, although all of them were not relativity, but yet Einstein wrote it in General Relativity, and it was written mid-1912 and early 13, and the notebook is used from both the ends, and we will soon see with entries meeting upside down about a quarter of the way through. So this document holds a monumental significance, and we are going to look into what that document is in the history of science, offering invaluable insights into the origins of the theory of general relativity. So this is actually the importance, and it is very, very important, those who are trying to understand general relativity, the genesis, how it started, etc. So first let me show you what the notebook looks like. So this is how the notebook looks like. So Einstein wrote in both direction, and there is the front cover. As you can see, it was Helen Dukas, Einstein's secretary, type descriptions of the notebook as notes for lectures on relativity. Now we will explore one by one the most important pages and how they contain the seed of general relativity. So the initial pages were a little bit kind of a different kind of a writing which I have skipped, but here you can see that the first when we go to the main page, we find serious physics. So what we find here is that Einstein recounted the elements of the four-dimensional approach to relativity and electrodynamics of Minkowski. So here I have highlighted it in red, and with my limited knowledge of German, it tells basically with the four space-time, so x, y, z, I, c, t, and x1, x2, x3, x4, and proceeding through these scalars, 4 vectors and 6 vectors, and the operations allowed with them. So this was the initial starting, apart from the cover page which I have showed, which was designed by Helen Dukas, his secretary. Now the next part that we move is very, very important because this part, which you can see ds square equals to this is basically the line element, and we will soon see it is nothing but the most important metric tensor. So you can see that initially Einstein wrote this metric tensor in capital with G capital mu nu. So the coefficients, this G mu nu, enable us to compute the spatiotemporal interval and ds between events separated by infinitesimal coordinate differences dx mu nu. So you understand that this is the most important, the metric tensor. Now if these coefficients assign spatiotemporal intervals that do not conform to flat geometry, then Einstein have captured the full range of gravitational effects in the manner of Einstein's relativity. And as you can see here, that it actually enables us to compute the spatiotemporal interval, which I was telling, ds being the infinitesimal distance. Now as we know that today that the metric tensor is basically the famous G mu nu, so Einstein later shifted this capital G mu nu to small g mu nu, and the big project now is to find how this quantity G mu nu, the metric tensor, is generated by source masses. So these are the gravitational field equation, that is, this theory is analog, I would say, to Newton's inverse square law of gravity. So the lower half of the page, if you zoom it later, you will see that it clearly marks some rudimentary efforts in that direction. So what Einstein was trying that to apply the gravitational field equation from his earlier Prague 1920 theory of gravitational fields, because that has to be something which is similar to Newton's inverse square law of gravity. Now it continues. I mean to say, I have skipped all the pages of the manuscript, not all of them. So Einstein's analysis continues at this simple level on the facing page, and here you can see this is in German. He asks the question. He looks at the coordinate divergence of the metric tensor and asks, "Ist thy invariant?" or "Is this invariant?" And as the computation that follows, it shows obviously it is not. So how these quantities transform under changes of coordinates is clearly a major focus of his analysis. And what is most important, what is noticeable, is that Einstein has not yet used any of the technique of the Ricci and the Levi-Civita absolute differential calculus, which we now know as tensor calculus. Instead, what he uses this phi, the old method, in order to transform the invariant quantities in a form of a scalar phi. So indeed this is beautiful, because the manuscript, and we are actually living through that era when Einstein was trying to find out why it is not matching the problem with the scalar function, and he was not using the tensor calculus. So from here what we do is that we go to this page. Now what does this page actually denotes? Now here you will see that Einstein finds several of the key notions of the new theory in an unexpected arena, which is classical physics. What Einstein does is to re-derive a standard result in the classical physics. This one, which I have just marked in red, this portion, it tells that if a mass is free to move inertially, except that it is constrained to move within a curved surface, what is the curve traced by the mass in that surface? Obviously you can understand that this is the hint of the geodesic, and it proves to be a geodesic of the surface of a curve is the shortest distance. Now if I go with the calculation part, as you can see, this one which I have highlighted, this is nothing but the geodesic equation which Einstein has written. And how the calculation starts: the surface is defined by a scalar field in space. It contains values, say, of t, such as f equals to 0. Now the equation of motion of a mass moving in the surface is just its acceleration vector, which is given by the ordinary partial differential equation, and this is proportional to the reaction force from the surface, which is orthogonal to the surface and proportional to the gradient, which is actually given by the partial differential equations. So you can see now the concept of geodesic is emerging. He is writing the geodesic, and Einstein is trying to find out that particular equation through this manuscript. Now after that there are around 9 actually pages which goes on with the calculations, which I have mixed. What is important is that after 9 pages like this, Einstein starts a new heading. It is a new heading, and it is called the gravitation. So you can see this, and we are thrown actually into the real part of general relativity. Now on this page, Einstein sets up the equation for conservation of energy and momentum for a continuous matter in general relativity. So he actually, as you can see, I have just magnified the portion from the manuscript with the equation of motion for a point mass, the geodesic equation, but now it is actually written in the Euler-Lagrange equation. He then actually applies this to a cloud of non-interacting dust particles. Now you might ask the question, why it is non-interacting? Just to make things easier, I'm going to say exact solutions in a free fall to arrive what we now recognize to the condition of the vanishing of the covariant divergence of the stress energy tensor T mu nu. So this is how he starts with the geodesic equation, writes it in the Euler-Lagrange equation, applies it to the non-interactive dust particles so that things become easier, and the derivation we now define is finally the stress energy tensor. Now there is a good amount of evidence that Einstein's knowledge of tensor calculus is still limited, and he does not know or he was not sure that the operator acting on T mu nu in this occasion is generally the covariant operator. So this T mu nu is actually, he was confused at whether this is a covariant operator or not. And in order to check the covariant operator, he replaces the T mu nu with the metric tensor G mu nu and sees whether the result is 0 or a 4 vector, right? And as it showed to be, if the operator is generally covariant, he proves it to be 0. And this one, which I have just underlined here, it tells stimmt, the German word for correct. So this is how he represses and trying to find out the covariant nature. So here now you can see that what is noticeable, that due to the absence of the techniques of Ricci and Levi-Civita for producing invariant quantities from the derivatives of the metric tensor, because he did not know, so that lacuna is filled with more pages. This one that Einstein writes, the 4 index symbol. I know it is small, but later you can zoom the video and see it. This is the 4 index symbol notation, I, K and LM here. And it goes on repeating here, here, and in several places. So, there is no indication of the 4th rank Riemann curvature tensor, as we know, which would have been the major part, but it is not there. So, which we now recognize as a crucial idea, it was not there. And it was during this time that we know that the story tells that Einstein only learned these methods of Ricci and Levi-Civita through his school friend, mathematician Marcel Grossmann, a master of differential geometry. It is Grossmann who went to the library in search of methods that would accommodate the arbitrary coordinate system, and he found Ricci and Levi-Civita's article of 1901 with the Riemann tensor and reported. So here you can see it is written Grossmann and his name and the tensor 4th rank. And here Einstein actually contracted the 4th rank Riemann tensor to produce the 2nd rank Ricci tensor. Now you see in a few of my videos on Einstein field equation have shown that it is a contraction. Now you can really see the historical part unfolding in front of you, that it is in this particular equation that he contracted and he found the 2nd rank Ricci tensor. And most importantly, you will see that if it is serving to the gravitation and tensor, obviously it must reduce in the weak field to a Newtonian form. And this is where he writes that sollte verschwinden. I am very sorry for my horrible German pronunciation, which means it should vanish. Einstein noted this condition in weak field forms, it should vanish. So here he writes that sollte verschwinden, this one, it is written in German in his writing as it should vanish. Now, once he has written all those solutions, finding a solution to eliminate all these 3 terms in the weak field limit is actually emerging to be a very difficult challenge. And here you can see it is more or less most of the equations here are written in a clear manner. So with the absence of knowledge regarding the Riemann curvature tensor, what Einstein did is just like a child, he would proceed to laboriously manipulate the extensive expression. And you know, if you see the other pages of the manuscript, he just writes all those complicated equations page after page, and his frustration grew. And it became palpable as he struggles to navigate through those growing stacks of complicated symbols. And he expresses this here. And I won't pronounce it again in German. It is saying it's too complicated. So the rest of the pages, as you can see, that it is all writing these equations in a nice manner. But all those big mathematical symbols came to him as too complicated. So because it is too complicated, so Einstein have to abandon the Zurich paper, and as I have already given a hint that he went to Marcel Grossmann in order to find out a better solution, and from Prague he went to Zurich, and this is what we are going now to look into, the most important, the seminal paper which actually accounted the extensive usage of tensor calculus and formation of the original theory of general relativity. This one, the Entwurf document, or in English it is translated as Outline of a Generalized Theory of Gravity and of a Theory of Gravitation. First we will look into what overall this Entwurf document tells about. So as you can see, this is actually the Entwurf document, and this is the title in German. So it is basically a collaborative effort of Einstein and Grossmann. It actually laid the groundwork for the final theory of relativity. Now this paper actually introduced what we call now the concept of general covariance, a crucial principle which tells that the laws of physics should be invariant regardless of the observer's frame of reference. And as we will explore, that this is the paper which contains all the essential documents and laid the foundation of general relativity. But most importantly, how important it is in our understanding of physics, let us understand. Now, you must have heard about Norman Foster and Norman Foster Ramsey Jr. Now, he tells that this is one of the turning points in the developments of relativity. So you can mark those which are written in red, that Einstein realized that he cannot proceed further, and with the help of Marcel Grossmann, he supplied using the Tensor Calculus, and they were able to write this in a proper mathematical representation. And the tenfold expansion, what is the tenfold expansion? That is the metric tensor, which I have already explained in few of my videos in field equation. From Newton's single gravitation potential, but Einstein, with the problems of physical intervention, was unable to solve this. So he backed away from the necessity of considering 10 corresponding field equations. And we know that this is actually 16 equations minus 6, 10 equations forming into one. So from here, what we do is that we move into the real paper. Now you see in German, it is actually divided into two parts. I mean to say the entire project. So Physikalische Teil von Albert Einstein, that means the physical part is taken by Einstein and the mathematical part is taken by Marcel Grossmann. So right at the beginning of the paper, we see that it is quite well divided into two parts. Albert Einstein taking part of the physics and mathematics taken care by Marcel Grossmann. Now, when Einstein arrived in Zurich in early August, he was convinced that a metric field, I would say, of space-time, which generalizing to the Minkowski matrix to pseudo-Riemannian dynamical metric, was the right relativistic generalization of Newton's potential. The main question which arises was to find the basic equation for this field, but how to achieve this was in the dark, and he looked for mathematical help to Marcel Grossmann. And his old friend was now also a professor of ETH, and Einstein succeeded in gaining him as a collaborator in his search for the gravitational field equation. And as you see here, that as we turn the pages of history, Einstein has himself acknowledged the fact, when I put problem to investigate general covariant tensors whose components depend on the derivatives of coefficient of the quadratic fundamental, I was made aware by Grossmann about Ricci, Levi-Civita and so on. And you see he recounts beautifully. He at once caught fire, although as a mathematician he had a somewhat skeptical stance towards physics. He went through the literature and in particular Riemann and Ricci. This entire development was connected to the Gaussian theory of curved surfaces, in which for the first time systematic use was made of generalized coordinates. So it's a kind of a reminiscence. So Einstein really recounting that how Grossmann went to the library, found out the books and helped him. One of Einstein's friend, Louis Crollo, I am again apologizing for my German pronunciation, spoke to Grossmann about his troubles, and Louis Crollo tells that Einstein told that Grossmann, you must help me, otherwise I will grow crazy. So it is really fascinating to study these researches, because one can see Einstein at work and theoretical physics at its best, a delicate interplay between physical reasoning based on an intuitive estimate of the most relevant empirical facts, equally important to construct the mathematical aspects and requirements. So in this paper, as we will explore, Einstein came very close to his final theory, but physical and conceptual arguments that we will discuss convinced him for a long time, and with a heavy heart, he writes to Lorentz, he had to abandon the general covariance of the gravitational field. So the Einstein-Grossmann theory actually contains all the essential elements of Einstein's definite theory of gravitation. What are the essential elements? Coming up into the next part of our video. So the first was that the space-time of Minkowski is generalized to embrace the wider phenomena, obviously the gravitational phenomena, and which we call the curvature of space-time. Then comes the key question of the gravitational field equation. Here things started, at least in the mathematical part taken by ahead by Grossmann. And from a mathematical perspective, the place to start was the Riemann curvature tensor. It is the measure of the curvature of the different areas in the space-time. So if I show you, this is the typical kind of a page or writing of the Entwurf paper. So the question comes, is the gravitational field equation, as again with my German I have translated this part. So this IKLM, which I showed you earlier, the indices. Now, so here what he writes is that Grossmann introduced the Christopher 4 index symbol of the first kind. Now, as you know, I have also demonstrated in my earlier videos that there are two types of Christopher symbols, the first kind and second kind. So the first kind is basically this IKLM, and he then performed the mathematical operation of contracting which yields to GIM, this one. Again, let me highlight it. It's so small, I understand. So this quantity, which we called, is almost the Einstein tensor. And the place to start with is the Riemann curvature tensor. It is the quantity that measures the curvature. So one condition which actually the new equation must satisfy, obviously it must return to the Newtonian results under the ordinary conditions. Now, as you understand that when Einstein is generalizing special theory to general theory, so under weak field approximation, when I mean to say gravitation and things are going quite slow, what would happen? It would again go back to the Newtonian results, isn't it? So now the question is that why they are not taken. I mean to say one condition which was not taken into areas. Now why they are not taken, we will just explore in right now. So I have highlighted this again for the manuscript, and in German actually it is written that, however, it turns out this tensor does not reduce. That means it does not turn down to the Newtonian expression of this phi in the case of infinitely weak static gravitational fields. This is the problem. That if the general theory of relativity is persisting and it is consistent, obviously it will go back to its predecessor, that is the Newtonian theory. And here Grossmann writes that this is something which is not reducing to Newtonian expression. So it means that Grossmann stated that the equations in question do not seamlessly transit back to Newton's theory. That is basically the problem. So there is a fundamental issue in how this reconciliation with Newtonian mechanics and relativity would be done. In the next page, we also find that this var theta mu nu is referred to as the contravariant stress energy tensor, and which is actually denoted by T mu nu, and each of these operators yields a tensor of the same type. And this part which I have just highlighted, this one in red, in German it actually tells that thus one recognizes the stress energy tensor var theta mu nu of the gravitational field enters the conservation law for the gravitational field exactly the same way as the tensor of the material in the conservation law of this process. A remarkable circumstance in the divergence of the derivation of both laws. So these are, as you understand, mathematical proceedings, mathematical calculations. We are not going into that, but this is how the entire theory began. So what is the issues that we faced in Newtonian theory? So if you remove those issues, how the theory will be consistent? So let us look into this part of the video, that what are the requirements to be satisfied. Simple. The theory must reduce to Newtonian limit for weak fields and slow moving matter. There should be a conservation laws for energy and momentum, obviously, without which the laws of physics will fail. The equivalence principle, which Einstein's famous thought experiment, that must be embodied and it must be there. And the theory respects a generalized principle of relativity to accelerating frames when we take into account the gravitation and inertia and the metric field G mu nu. Einstein expressed this by the requirement of the general covariance of the basic equations. So this is actually the requirements, and in due process of time the theory definitely I would say they are definitely met with those requirements in order to become a consistent theory. So can we summarize the entire Entwurf thesis paper between Grossmann and Einstein? Let us look into the next part of the video. Here is the summary of the Entwurf paper in very simple language, the overall idea of this paper. This paper introduces the concept of equivalence principle, obviously, which states that the effects of gravity are indistinguishable from the effects of gravitation, and the principle had profound implication for our understanding of nature of gravity. Einstein and Grossmann employed the mathematical framework of Riemann geometry to describe the geometry of space-time, the four-dimensional fabric of space-time, and this allowed them to express gravity as a curvature of space-time. One of the key features emphasized is the general covariance, which state that the laws of physics should remain unchanged under arbitrary coordinate transformations. And the paper presents field equations that describe the gravitational field. These equations are precursor versions to the final field equations of general relativity. Apart from this, we see that there is a comparison. Einstein contrasts his new theory with classical Newtonian gravity, highlighting its ability to account for relativistic effects such as the bending of the light and precession of the Mercury's perihelion, which is coming up very soon. This paper also discusses potential experimental consequences of the new theory, suggesting that it could be tested through astronomical observations and gravitational lensing. And finally, yes, Einstein, Grossmann, and Entwurf emphasizes geometric interpretation of gravity, which is a curvature of space-time, which is determined by the distribution of matter and energy. So overall, what we can say is this. The paper was a seminal paper that revolutionized our understanding of gravity and space-time. It established general relativity as a cornerstone of modern physics with far-reaching implications for cosmology, astrophysics, and our understanding of the universe. Now we have to, from here, we have to move into the third and the most important paper. Both, as you can see, a friend in need is a friend indeed, and Grossmann, being a friend, came into use when Einstein needed him best. Another friend, again I would use the same quotation, a friend in need is a friend indeed, was the Italian engineer and mathematician Michele Besso, or Michel Besso. And now we are going to look into the Einstein Besso manuscript, which also made a formidable change and change our understanding of the physics. So now this is the paper, the Einstein Besso manuscript, a collaborative document created by Einstein and Michele Besso. Here is their picture. I mean, we have only one picture, unfortunately, of Einstein and Besso over the internet. So this is basically the collaboration between Einstein and Besso. It is actually compilation of the approximately 50 pages calculations, half of them by Einstein, half of them by Besso, and it actually is the calculation of the precession of the perihelion of Mercury, and it actually uses the field equation from the previous Entwurf theory, and this is how okay, now this right now, which you can see on the screen, I'm going to show you what actually this is. Okay, so we move into the paper, and the first page actually looks like this, and Einstein derives here the gravitational field of the sun. And then this is a schematic diagram representing the precession of the perihelion Mercury, which shows a gradual, very small shift in the orientation of the orbital axis with each rotation around the sun. Now these two friends were actually, I would say, a close friend and confidant of Albert Einstein. They actually met at Zurich in the late 1890s. They worked together at the Swiss Patent Office in Bern, and now Besso went as an engineer, and Einstein remarked on his academic career. And in 1912, he was appointed full professor at the alma mater, the Polytechnical School, now ETH at Zurich. Now, this perihelion calculation precession of Mercury, this is also an important part of general relativity. So what happens is that according to this theory, large masses curve the space-time around them. We know that. And while smaller masses follow the straightest possible path in the curved space-time. And the examples of such paths are the orbits of the planets around the sun, and orbits predicted by Einstein's theory are very nearly but not quite the same as those predicted by Newton. So the Newtonian theory, as you can see here, had a trouble accounting for the motion of Mercury's perihelion. So the point of its orbit is closest to the sun. So, and over the course, over the course of the century, this perihelion motion adds up to about 550 seconds of arc. So we know that a full circle is 360 degrees, a degree is 60 minutes and a minute is 60 seconds. So 550 seconds of arc is very tiny effect. More than I would say, moreover, more than 90% of it could be chalked up by due to the gravitational pull of Mercury by other planets. Yet a gap of about 43 seconds remained, which Einstein hoped his new theory could find out. So here you can see this speeds up the orbit, and here this is the Einstein precession orbit, and it comes closer to the sun a little earlier on a different ellipse. So that was basically the calculation, and this, as you can see now, this one which I have shown, now I highlight it in blue. This is the end result of the manuscript, is 1821 seconds, which is 30 minutes of arc, as you can see, Einstein's own handwriting, more than 3 times of the total motion of Mercury's perihelion. But this is not the end of the story. What he tried is to make his theory yield in a few more seconds in other ways, but he came up empty. I mean, he said there was no solution. And later, as you can see, in November 1915, he changed the equations determining how matter curves space-time, and he and Besso had used thereby arriving what we know as General Theory of Relativity. And most strikingly, you will see that Einstein re-performed the calculations he had previously done with Besso, as he later recalled that he experienced tremendous heart palpitations because when the sought after 43 seconds ultimately emerged from the results. Brilliant. So he calculated earlier, then he went back and concentrated more into the gravitation theory. Again, using this and Besso's calculation, he was actually thinking or guessing that ultimately the 43 seconds should come up. Again, otherwise the theory is irrelevant. And he experienced this heart palpitation because finally, after 43 seconds, the results emerged. Now we have to travel, I don't know what would be the real kilometer in terms from Zurich back to, I would say, Berlin, and really something is happening at Berlin. I won't say what is happening, but something really important was happening at Berlin. Now, Max Planck was a German physicist, best known for his originating quantum theory. Walther Nernst was a German chemist who formulated the third law of thermodynamics. Emil Warburg was a German physicist known for his research in magnetism and gas discharge. And Heinrich Rubens was a German physicist celebrated for his precise measurement of thermal radiation. Now, you might be thinking that why I am mentioning the name of all those 4 people. Because apart from that, there was another famous chemist and a physicist, Fritz Haber. And he wrote a letter, and in this letter he writes, Einstein's closest colleague is Herr Planck, and then Herr Emil Warburg, and Herr Heinrich Rubens, who also work in disciplines related to his specialty. Now, why is he writing? Whom is he writing? I mean, to say, why Fritz Haber is mentioning the name of Planck and Walther Nernst? Now, in January 1913, Fritz Haber wrote to Hugo Kruse, who was a worker at the then Prussian Ministry of Education, of his thoughts about Einstein, bringing him back to the Kaiser Wilhelm Institute of Berlin. This is the Kaiser Wilhelm Institute of Chemistry back in 1930s. And Einstein was totally unaware because he was too busy sitting at ETH in Zurich and working on his new gravitation theory. Now, who is Fritz Haber? Who is Hugo Kruse? Why is he writing a letter to the Prussian Academy? Why is he mentioning the name of Max Planck, Nernst, Emil Warburg, and so on? What is the plan behind bringing Einstein back to Zurich? All these things we will cover into the next part of the video. Yes, we will take a pause now in the second part where this letter is written and Einstein, totally unaware, is totally submerged in his own calculations of gravity with Michele Besso and the Entwurf theory. And we will see in the next part of the video why is this letter important and will Einstein's travel from Zurich to Berlin and what would be the final effect. So that's all for today's video, and I would like to immensely thank you for taking your time to watch today's video. If you have liked the video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Student. This is my email ID, and this is my other channel where I put up videos only to General Theory of Relativity. And further, you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. We will soon see you in the third next part, where we would see that whether Einstein would be traveling from Zurich back to his town in Berlin, and what would the shape of general relativity would eventually lead into. Physics for Students will be back with few more and keep on producing more quality content and videos on physics and mathematics. But till then, very goodbye.